Hello, and welcome to my video introducing logarithms. I'm often asked, why do they exist? Why do we need to learn them, as arithmetic is so easy on a calculator? The answer goes back to the early 17th century, when people needed to perform a lot of manual calculations, as science was moving on at that time with telescopes becoming commercially available, and the types of calculations were becoming complicated. A more efficient system was needed, and this led two mathematicians, Napier and Bürgi, independently developing logarithms around 1610, building on standard form, which had been used since the 9th century to handle larger numbers, but logarithms allowed them to greatly reduce the time needed to multiply, divide, and take roots of numbers. This led very quickly to the development of lookup tables, and then to slide rules, the pocket calculator for nearly 3 centuries. So that answers why they were created. But they've been superseded by digital calculators, so why do we still learn them? Well, there are two reasons. The first is modelling nonlinear systems occurring in nature. Let's take for an example COVID, a very topical subject, and the R number, and how that affects growth within a population. This is a logarithmic relationship. And we can also consider something like radioactive decay, where the half-life can be modelled, and again it's a logarithmic relationship. Secondly, as natural logarithms to base e, they continue to be very useful in calculus. Let's look at an example comparing the masses of the Earth and the Moon. Here are some modern numbers, based in kilograms, but the method is the same. The log of the Earth's mass is 24.776, and the log of the Moon's mass is 22.866. Then we subtract these to get 1.91. We need to take the antilog of this, and hence the actual answer for is equal to 81.3. The Earth is 81 times heavier than the Moon. Now the question is, where did those numbers come from, and why did we subtract them? The answer to this is the strong link between logarithms and exponents. This link here is really important, and the use of laws of indices is what underlies the laws of logarithms. So these two are also closely linked. Let's look at the same example in more detail. Starting with the mass of the Earth, 5.97 times 10 to the 24, the way the logarithms work is to ask 10 to the power of what is equal to 5.97. This is 0.776, i.e. 10 to the 0.776 is equal to 5.97. And then we multiply this by 10 to 24. And we know from the laws of indices to add powers when multiplying, giving 10 to the power of 24.776. Similarly, the mass of the Moon, 7.347 times 10 to the 22 kilograms, written as powers of 10, gives 10 to the power 0.866 times 10 to the 22. Adding the indices, this is 10 to the power of 22.866. Finally, we need to divide these. Since when dividing powers are subtracted, we do the same with logarithms. 24.776 subtract 22.866, and our division becomes a much simpler subtraction, giving 10 to the power 1.910. But we need that as a number we recognise a lot more easily, so we calculate that as 81.3. So that's the addition being equivalent to multiplication dealt with, and the subtraction being equivalent to division. Now let's look at the third law. The log of x to the power k is equal to k times the log of x in terms of indices, using an example, the cube root of 8.34. We know that using indices this can also be written as 8.34 to the power of 1/3. And similar to the previous examples, we write this as 10 to the power 0.921 to the power of a third. By laws of indices, we multiply the indices, here dividing by 3, giving 10 to the power 0.307, and that is equal to 2.03. Repeating this example using logarithms, the log to base 10 of 8.34 is equal to 0.921, and to find the cube root, we divide this by 3, giving 0.307. We then convert this back by taking the inverse log. 10 to the power 0.307 is equal to 0.203, as we expected from our working with indices. These examples have demonstrated that the laws of indices and logarithms are equivalent rules applied in different formats. When working with logarithms, we're manipulating the indices of numbers of the same base, temporarily outside that base, before converting back to normal numbers. Now we move on to number bases. It's important to realise that the laws of logarithms require the same number base applied to each term, and throughout this video we've used log base 10 as this is the most familiar one, as it fits very well with standard form, and that's how it was used traditionally for manual calculations. However, other number bases can be used, typically for practice and gaining familiarity with the laws. The main contemporary use is base E, known as natural logarithms, that are particularly used in calculus, but that's an entirely separate video for next year.